Start. Thanks again for everyone to come here in person and online to this IEEE seminar. And today we're very pleased to have our distinguished lecturer from the Signal Processing Society IEEE to visit us, Professor Wong Song Gan. And he is a professor from Nanyang Technology University from Singapore. And he's a professor of audio processing and director of the Smart Nation Lab in the School of Electrical and Electronic Engineering at Nanyang Technological University, Singapore. He received his Bachelor of Engineering and a PhD degree, both in electrical and electronic engineering from the University of Strathclyde from UK in 1989 and 1983, respectively. And he joined the faculty of Nanyang Technological University as a lecturer in 1993. He also served as the head of the Information Engineering Division from 2011 and 2014, and the director of the Center for Infocom Technology at Nanyang Technology University. So Professor Gan serves lots of positions in the society and magazine. For the sake of time, I will not read all of them. And his research mainly has been concerned with the connections between the physical world, signal processing and machine learning, sound control, which resulted in a practical demonstration and the licensing of spatial audio algorithms. Psychoacoustic signal processing applied to the soundscape, evaluation, audio intelligence monitoring at the edge, and active noise control for headphones and open apertures. So today, Professor Gan will have her talk about augmented mixed reality audio for hearables. And by the way, after talk, we'll have dinner with speaker, Professor Gan, at the Chester's Kitchen, a restaurant close here. Everyone is welcome to join us. With that, and please join me to welcome Professor Gan.
Thank you, Richard. Thank you. Thanks, everyone. Okay, good evening, everyone. Welcome. Very glad to be here in Rochester's presenting this distinguished lecture talk on augmented and mixed reality audio for hearables. So my name is Woon Seng. I come from the Nanyang Technological University. A lot of people often mistaken this is in China, okay? But it's in Singapore. I hope you know where Singapore, very small countries, right at the tip of the Malaysian peninsula. But anyway, let's talk about this topic on augmented mixed reality audio. And this work is basically a collaboration work with Professor Brandenburg. I think you may have heard of him as inventors of MP3. And also Professor Välimäki from Finland. So we look into how we can integrate all the sensing, control, and the rendering parts into these hearables. So hearables, you can think of it as smart headphones. By the way, I know that any one of you are working in audio processing related topics? A show of hand, anyone? So no, I will try to help you to understand this topic. I know there will be some mathematical equation, but I'll try to tune it down and so that you can understand the meaning of all this work. Okay, and feel free to interrupt me during the talk, and if you have questions related to my explanation. Okay. Get back. Okay. This is first of all introduction of my university. This is a bird's eye view of the university campus. You can see several buildings, and NTU is one of the two comprehensive universities in Singapore, the other being the National University of Singapore. All right, And I'm working in the School of Electrical Electronic Engineering and also directors of this Smart Nation Translab. So in the lab, we have facilities to conduct all sorts of spatial audio experiments. You can see loudspeakers, you can see headphones, and you can see all the measuring tools that we use to do some of these studies. And in this talk, I will be explaining some of this work as well. But I would just want to share with you some other works that I've been working on. First of all, on smart sound sensing. So we built some of the sensors that can be deployed in the public areas to sense the sound direction, the sound classification, the sound class of an event. So there are some government agencies who need to know what type of noise that the residents are complaining. So they need to have hard evidence. So we need to build some smart sensing box that can be deployed. I will not be talking about this, but rather on another topic, that how do we capture what we call the head-related transfer function. I will talk more about this later. And another topic that I'm working on with my researchers is on artificial intelligence for sound. So this is a hot topic, applying AI to many disciplines nowadays. So AI for sound, we want to find out where the sound is coming from, what type of sound events, what type of information we can extract from the surrounding, either indoor or outdoor. And this is the work that I have talked about in the Twin City sections. Is on active noise control. So basically, you have heard of all these active noise control headphones. We are using noise to fight noise. So we generate anti-noise to fight the noise. So we've done some work related to build all these type of speakers in a windows, and so using generating anti-noise to basically cancel out the noise that comes into the building. Okay, but I will not be talking about active noise control here. Rather, I'll be talking more about spatial audio rendering. How do we use headphones and listen to surround sound, or more than surround sound? It's what we call spatial sound. Sound that can be positioned, sound objects can be positioned anywhere in a 360 manner. How can we do this type of rendering? So I'll be talking more on that. So today's topics consists of 3 parts. The first part is to give you some motivation on why we need this type of spatial sound in audio, in our hearables, and especially nowadays we have all the head-mounted devices. I think you have seen the Apple Vision Pro devices. That devices basically transport you to a virtual or environment that can manipulate objects in the surrounding. But there's something lacking here, is the spatial audio effect. So I'll explain more about that type of application. And to give you an overall framework on how we can use signal processing techniques and AI models to help us to build this type of intelligence into these hearables. So I will dive into the details on how we can do sensing, control, real sound control, and also rendering. Okay. Then I will end the talk with a conclusion and some of the new topic or advancement that people are now working on this area. So the first, to start with introduction. So before I start with the introduction, I will give some definitions of what is augmented reality, and what is mixed reality, and what is virtual reality. So you can see there are 3 domains. Virtual reality is at the one extreme, while augmented reality is at the other extreme. So virtual reality means that we are transporting the user to a digital environment. You wear the goggles, you are basically, you can see pixelated, you are in this environment which is basically built of pixel, and they are representing the environment in the virtual sense. Okay? So you can interact, you can walk around, but it's not you. You have an avatar inside this environment walking around. And at the other extreme, you have the augmented reality. I believe you know Pokemon Go, this type of thing. And basically, they are basically putting some tag or some labels in a real environment. For example, if you use your cameras, position it at some buildings, it will indicate what is this building and other information. So they are putting some labels into the real environment. But in between, the mixed reality is where things get very interesting, is where you mix the real and the virtual objects in an interactive and cohesive manner. All right, there's a mixed reality. So how do you do that? Okay, how do you do that? You can do that in visually, but you also need to do that in audio. And oftentimes, audio have been neglected in most of this style application. People are just looking at vision. But if you look at it, without the audio, without the, people just use stereo, or even they don't care about audio, you lost that engagement, you lost that emotional engagement of this virtual reality or augmented reality playback. So audio is an important component, but often is neglected. So we are trying to share with you that there are important things that you need to include into this reality. So if you look at all these applications, ranging from learning experience, entertainments, even military simulators, and also some communication, navigation, and some safety device to guide those visually impaired in the environment. Spatial audio can play an important role to enhance the interaction, to improve the response time. For example, in the simulator, for soldiers to improve their response time in reacting to different situations. They know the direction where the sound is coming from, where the firing is coming from. It's also used in gaming as well. All right. So spatial audio has its purpose here. And also in navigation, it can give you a more seamless integration environment. It will guide the users to travel around in the city. All right. So spatial audios, being the audio cues that can guide the users, are very important. So if you look at now, you see all these devices, gadgets, hearables. They come in all shapes and size. You can see on one end, you have the over-the-ear, those headphones that are cupping the ears. You can see on the ear, they're just touching the ear surface, okay, but it's not cupping the whole ears per se. And we have also those head-mounted devices, like the Apple Vision Pro and others types of goggle from Meta, from other companies. Basically, they are using some micro speaker to fire the sound. So they leave the ear open so that they are aware of the environment. And they also have the different types of in-ear. These are in-ear type of device, and also earbuds. So it comes with different form, shapes, and size. And within all these hearables, we have some common features that are integrated into the hearables, being the active noise control, acoustic transparency, ambient sound sensing, etc. So we all know the purpose of having active noise control, basically to quiet the environment. All right? And acoustic hear-through means that you want the sound to come in from the environment even though you are wearing a headphones. So because once you wear the headphones, you are basically cut off to a certain extent of the environment. So you want that kind of natural hearing to come in. How do we do that? All right. So I will share with you a techniques that can do all this type of hear-through. And of course, there are other types of features that can be integrated. And nowadays, we also have sensors that can detect the gait analysis, the movement. And this can be used for training the athletes to run better and so on. And there are also sensors that sense the pulse, the heartbeats, whatever. By wearing a hearable, they have sensors to do that. And they can detect your internal biosignals. And these are also very important so that you can tell whether someone is not feeling well or have a certain state of emotions, etc. All right. So they are integrating a lot of sensors into the hearables. All right. So, and you can see that roughly there's open headphones or closed headphone. There are two types. All right. From this, you can see that some of them is just cupping the ears and basically cut off most of the ambient sound, but the others will allow sound to get through into it. So we'll be talking more about these two types of headphones, hearables. And this is a very interesting survey done in 2019. It states that on average, consumer owns around 2.4 hearables, 2.4 pairs of hearables. They have different shape and size hearable. But this was done in 2019, before the COVID period, pandemic. So you imagine that nowadays, more people are buying, during the COVID period, people are buying more of these hearables to work from home, all right? And these numbers are maybe more than 2.4. And you also, another interesting survey results that's shown from here is that they are willing to sacrifice 24% of the battery life just in exchange of some smart features, AI features. In other words, they are willing to sacrifice 2 hours of their listening time. Instead of having 8 hours, they only have 6 hours of the listening time. So because people's expectation of these smart devices are that they want to have some smartness into their hearables because they are used to having smartphones, smart speakers, and smart devices all over the place. So the expectation of these hearables will also need to be smart. And there are many other things from these surveys that they recognize the importance of sound. They want to have some smart features that's built into this device as well. All right, so why special features needed for hearables? So if you look at this situation, if you close your eyes, cup your ears, you're basically cup out most of your senses to the environment. So if you open your eyes, but still cupping the ears, you are just having the frontal vision view. You still do not have the entire 360 environmental sound, all right? So if you uncup your ears, you get your 360 sensors. But if in this case, it's in the cafeterias, that's just next to a busy roads, and you want to have some quiet. So if you use headphones, you use ANC mode, active noise control mode, you basically cut down the traffic noise. But this is not good enough because you are just cutting down everything as well. You are cutting down the ambience, you're cutting down all these other conversations with people and so on. So hearables will need to have some smartness in it, and we are now advocating that a hearable can be a remote control for your ears that can integrate some of these smart devices that allow you to pick and select the sound that you want to enhance. All right, for example, if you want to have a conference call with someone else, you want to have a very clear message with him, but at the same time, you also want to be aware of the environmental sound that's happening. All right, so how can we do this? Okay, we already see some of these features. For example, the transparency mode that I mentioned here, you can see real sounds are in the environment. People talking, dog barking, and other types of sound. But once you wear the hearables, you are basically blocking the ear canal. You are basically blocking most of this sound. So how can we use some of these techniques to bring the sound capture from the microphones, process it, and make it sound as if it is coming from the real source without wearing hearables, without wearing the hearables. So how do we do this type of transparency type of playback? And of course, you can have attenuation. So this is either you want to have transparency or attenuation. Attenuation means you cut down everything. All right, so you can do that with ANC, or you want to boost up, like hearing aids. You want to boost up all the sounds. But this is still not very good because you're boosting up the background noise as well. All right? And you have, if you have a way to say selectively, I want to boost up some of the sound that I want to hear, like I'm talking to someone else, I want to boost up the amplification of the people that he's talking. So this is like a human type of cocktail party effect, correct? You have the ability to focus on someone talking and then ignore the rest of the others, ignore others. All right. So there's way we can do this type of level augmentation as well. And what about transporting someone to another environment? Just say that you are in a room, you want to transport into an in a concert hall environment. So you need to add on some of the ambience, reverberation, echoes into the environment. So we can also do this type of environmental type of augmented sound. And then what about things are getting more interesting? We have virtual sound that can come in. So virtual sounds are not the actual sound that hear in the real world. It's basically created in the hearables. You want to project the virtual sound out of your head and meet with and basically interact with the real sound. So there's a virtual sound over there, and you can sort of combine the virtual sound and the real sound into a single soundscape environment. Okay, so basically these are various modes that you can integrate into the hearables. And I'm just trying to say that there are different types of features that you can try to do this type of playback. So we have developed a framework to do this type of integration of sound and coming up with different processing methods to do this for the hearables. And this was published in the IEEE Signal Processing magazine in May 2022. If you're interested, you can take a look at this article. So in this article, what we do is that we break down the processing into 3 parts. So if you look at this diagram, we have the real acoustic environment in the real world. We also have the virtual acoustic scene that we want to introduce into the real world. So why do we want to do that? Because we can have this virtual assistant or virtual guides to help us to navigate in the environment. Okay, so we can play back this virtual sound in the hearables. And together, they goes into this smart sensing device. You can think of it as a front-end module, taking the information from the environment as well into taking into account of what is the virtual sound object you want to introduce into the environment. And these virtual sensors, I will elaborate more. How do we do all this sensing, smart sensing? And this smart sensing will derive the sound that we want to amplify, we want to attenuate, we want to do a hear-through, pass-through, or something like that. So this is what we call the real sound control. How do we process this style of real sound and make it what we want? And then together with the virtual sound, we combine this virtual and real sound together and come up with this active AR/MR sound. So this active AR/MR sound will go through this hearable, the earbud, for example, and they will be listened, they will be plugged into the ear for the user to experience this mixture of real and virtual sound in the environment. But one thing I want to emphasize here is that when you are plugging the hearables into the ear, there's also leakage. You cannot have a very close coupling. You wear the hearables, there's always not tightly fit most of the time, all right? So there'll be leakage that goes into the ear. And this leakage will cause problem. All right, so how do we counter these style of effects? Okay, so let's look at the first part, the sound sensing. Okay, so if you look at the sound sensing, nowadays the phone like the Apple, AirPod Pro, Apple Pro Max, has many sensors, microphones that are built outside the ear cups. They're embedded into the ear cups. And these microphone arrays basically are sensing the information of the environment. Okay, but beside that, we also have other types of sensors like astrophotometers. If you turn your head left and right, it knows where you're facing in the environment. You also have other types of sensors like heartbeat rates, sensors, and other type of interactions, proximity sensors, for example. So many sensors are now integrated into the hearables, all right? And these sensors, we can derive important information, like where is the orientation, the hearable response, the user's response, and so on, okay? Where he's facing, and so on. And also from the microphones, we can detect where the real sound is coming from, the direction is coming from, the sound class is what type of sound is it, and etc. All right? And also, from the microphone, you can detect the environmental information. You can detect the reverberations, the echoes. It's all captured by the microphones. So we can tell how big is this room by just looking at the acoustic signature. All right? So there are many informations that can be extracted from the acoustic sensors. So today's focus is more acoustic sensors. I'm not going into more details on other types of sensors. So, but there's also challenge in acoustic sensing. If you look at the acoustic sensing, it's so wide. There's so many things you can capture using microphones. All right? And all these informations are not bounded. They do not have a spectral or hierarchical structure. Unlike music or speech, they all have a certain structure we can exploit to capture the information. But environmental sensing through acoustic sensors is challenging because it doesn't have this type of structures and is often unbounded. And some of the sound that we receive from the microphone, it's very hard for us to differentiate whether, what is it? For example, it may be an alarm sound, but it can also sound like a bird song, bird call. All right, so there's sometimes the alarm sound and the bird call can be quite confusing, okay? So there are some similarity in some of these sound sources. And of course, they are all different types of sound sources in our environment. They all mix together and captured by the microphone of our hearables. So it's also very hard for us to separate them. Okay? And also, it's very difficult to know the sound is a foreground or background sound. Even for human, it's very hard for us to detect which is a sound that is foreground and which is a background sound. So in order for us to do intelligent systems, we need to build some AI models because the traditional DSP model has some limitation. Based on the models, they are not able to tell us precisely the information that we want. But for AI models, we can train, we can teach the model different types of classes of the sound, where is it coming from, and so on. So it can able to generalize the patterns of the acoustic signal. But in order to do this, we need a large database of sound sources, sound clips, data set. And this data set often are not well labeled. So for AI, I think most of you know that you need to have very good quality of data set. You need to be very well labeled data set. Tell the node, this is a bird sound, this is a human speech, this is a machine sound, and so on. You need to teach them. All right? And also, the sound sensors that we use in Singapore may be very different from the sound that we see here in New York City or in Rochester, because different cities have different characteristics of the soundscape. All right? So if you have one model that's built based on the sound that we collect in Singapore, you need to do some domain adaptation to move it to another city for it to work. All right? So there's also lots of fine-tuning, a lot of tweaking to work in different types of environment. So you can see from this list, I asked my PhD student to compile a list of freely open data sets for everyone. You can see that the largest data set is the one from Google. It's called the audio set, the one on top. It's based on the YouTube clips. They extract all the different data sets that people post in the YouTubes. All right, so this is very large, but these data sets are basically captured by users using their recording devices, using different medias. So it may be very hard to train train the model to apply it to different places as well. All right. So there are other data sets like the Urban Sound 8K. This is the data set from New York University. All right. They captured all this data set from the New York cities using their sensors that they built and planted in different parts of the New York City. All right. And for my work, we also built data set. It's called Singapura. These are all, Singapura is the older name of Singapore. We have these sensors. We basically plant them in some urban environment and capture the different sound data sets and use it to train our AI model. And we basically put it in an open domain for people to train it as well. Right. So you can see there are many different types of data sets and the number of samples you have, the duration of the data set, and where the location they are located and collected and so on. All right. So you can see on this side, some of these are weakly sound labeled, some are strongly labeled. So weakly sound labeled, they just briefly say that this whole track is like a city, and they do not go into the details of what are the sound elements in this track. So it may not be very useful to train using some of these weakly sound event label. All right? And to give you more information, nowadays we have competition or challenges. There's international challenges. It's called the detection and classification of acoustic scene events. So there are different style of challenges that they open up to the international researchers and scientists to submit their models or their results, that whether they can use their model to detect sound. For example, this is they want to tag the sound, whether this is a screen, a certain sign, or hits, or some key juggling. So it's recognizing different types of sound objects. So whether the system, their model can detect this type of sound objects. Others, like more challenging one, is to see where the sound is coming from, and also the sound class. For example, you have speech, dog barking, cars, and when is it occurring, and also the direction. There is azimuth and elevation included. And we can tell that the sound coming from which direction, what is the sound types, and etc. And I think there's also a more interesting one for machine fault detection. It's called the anonymous sound detection system. They will detect the machine sound, different type of machine sound, and predict whether the sound of this machine is it faulty or in a normal condition, and so on. All right, so there are many different types of challenges, and they are trying to push this boundary of innovation to see that we can build more smart sensing devices, okay, for hearables, for speakers, for some security traffic type application. It can be used in public areas to detect the flow of the traffic, to detect some of this anomalous case in the environment. Okay, and smart sensing has different components. You want to detect the direction, you can detect the class. You want to separate the sound. As I mentioned, sound are all aggregated into a single sensor point. You want to separate the sound into different streams, sound scene decomposition, etc. And you also want to recognize the environment where the users is in, whether it's in a large hall, whether it's in a very quiet place, or etc. So there are different purposes in all these requirements. This smart sensing helps us to better understand our local environment. And this has many types of applications. But today, my talk here, I just focus on this component called sound event localization and detection. So let me share with you what is this. Before that, this is a table that I compiled to show you that there are different techniques to do this type of sound event classification, detection, etc. And in the past, people will use the digital signal processing technique. You can see those in shaded. They are using some of these digital signal processing techniques. It works well, but it's not as good as the deep neural networks. Deep neural networks has really surpassed most of these signal processing techniques. So nowadays, people are just using the digital, the neural network techniques. So you can see from this chart, there are many different types of deep neural network techniques. This is from the website. And you can see there's a convolution neural networks, convolution recurrent neural networks, the UNets, the autoencoder, etc., even the transformer that's building for the LLM model. So there are many different shapes and sizes of the neural networks. You need to know how to choose them. But for some of the work that we are doing, we need to have a low-cost or lightweight solution. We cannot use a very complex one because it will not run on our embedded processor. All right? So here we are, especially for hearables, we are always very concerned about the weights, the power consumption, and the processing power. So this is the main block diagram showing you how we can do this type of intelligent sensing through microphone arrays. So in the front end, we extract features. So features being that we can take the spectrogram. I believe most of you have, we can take in some of this, turning into a time frequency axis, detecting some of the patterns in the spectrograms, or we can let the neural network train, recognize the features, some of the implicit features. Okay, so there are different approaches, but we would like to, we can combine whether you can handcraft features or using the neural network to detect the features. And once we have detect the features, we can move it to the next stage, which is the model filtering. So this part, we want to use some sort of a mask to separate the different sound so that we can differentiate sound A, sound B, and sound C through a so-called a time frequency mask. Okay? And we can also perform sound scene analysis to know that what is this environment. These are usually done through neural network. Okay, it's very complicated to do it in DSP, so it'll be done in neural network. All right. So at the output of the second stage, you'll notice you have a mask that can separate the different sound sources, and you also have a metadata that indicate this is a dog barking, this is a noise coming from vehicle, this is speech, etc. So we basically align the metadata with the separated sound. And to this, we go into the last stage, We go into the last stage, which we recover. We may need to do fine-tuning to basically get to the real sound source as clean as possible. So you can see the output is very informative. It consists of many information regarding our environment. So think of that. You only capture the raw data from the environment. The output of these smart sensing modules give you the real sound signals in different streams. For example, there are different sound types. And they give you a metadata that this is a siren coming at 150 degrees. This is a music occurring at 60 degrees, and the speech in front of you. All right? And they can even give some caption. It's a busy street, full of people, etc. All right? So if we think further, nowadays we can even use this as a prompt to prompt the neural network, the large language model, to give you a summary of the environment. All right? You can have these added features with these large language models. Yeah. Yes? Handcraft features, I will be talking about one of these handcraft features, like your spectrogram, like your interoral time difference, level difference. These are known mathematical model or so-called features that you can use some maths, like FFT, to derive these features. Of course, from the time domain, you really hardly know what is this signal all about. So you have to look at it in another domain. Yeah, I mean, but sometimes people just use the raw data and let the neural network train. But this will incur labeling. You need to tell it what is it and so on. All right? So the strategy is that if you really have a tight resource in your processors, you should have more handcraft features. Because usually for those neural networks, incur more complexities. You may not be able to run into your embedded processor. Yes, yes, yes. It's trying to replace the handcraft features, but provided you have the data set, you have a strongly data set. All right. If you have very small data set, usually you may overtrain it, and it will not be accurate in the inference part of it. Yeah, it's true. So there's always the consideration. Here we are looking for hearables, remember? So we always want to have a lightweight model. We cannot have very complex model that's basically operating in the cloud and so on. And this is something that we attempt to do it in our labs, all right? So instead of putting microphone in the hearables, now you can see from this, we have a planar circular microphone array. It may not be clear here, but in this circular PCB, you notice we have 6 microphones that's put at the circumferences of this array. Inside, in the center, there's 1 more microphone, altogether 7. So we captured all this signal through the microphone array, and we do the processing. All right, this processing can be an AI, can be a combination of AI and DSP technique. We can do some sort of directional arrival type of computation. I'll show you how this is done. And the output of this model will be sound classes. Is it falling? So they give you some probabilities that it's more likely it's a cough, maybe a scream, but it's not a falling sound. They will not be precisely, they always have these probabilities. So we can choose the highest one as the most likely sound classes. Okay? And same to the direction of arrival as well. Okay, so this type of task is called sound event localization and detection, SELD for short. Sound event localization, you need to do 2 tasks, localization and detection. And how can we do that? So we investigate, many people are working on that. We came up with our approach. This is called the sequential matching network. So basically, this is a hierarchical network, okay? If you look at it at one end, you have the sound event detection. This one in blue box. It basically classify what is a sound type. So they use some of this CRNN. But before that, they also put that into a feature. This is a log-mel spectrogram. They don't use the time domain signal. They convert into a log-mel spectrogram. And then they feed these neural networks and come up with the classes. Okay, come up with which is most likely. They have to train this, of course. Okay, usually we have lots of data to train this type of sound classes. But when it comes to directional arrival, usually this type of data set for directional arrival is very limited. Unless you set up equipment, go to the environment and pick up, where's the sound sources, and you do the recording, where is this sound coming from in the area. So usually it's very tedious. There's very less data on this in open data set as well. So usually we want to do something. We want to we go back to the digital signal processing approach. This is more signal processing approach. All right, we find the different directional arrival. We can use the histogram approach to find out what is the likely direction it's coming from. So these are all based on the DSP model. So from these 2 modules, we have the sound class, we have the DOA. We go into the higher up layer, okay, which combine all this information with their time, location, and so on. and go through these bidirectional gate recurrent units. Basically, this higher network is to try to combine, try to match, or try to correct any errors in all these modules, and come up with these sets of number of events, what is the sound events, where is it azimuth, which angles, and elevation. So these are the type of tasks, or these are the type of output that we want to derive from output of this model. All right, you can see many different things happening. And if you want to have more information of this is published in the ICAST 2020 some time back. And we also have other types of model that we built into a embedded system running in Raspberry Pi 4. All right, so this is one of another model that we use a deep neural network to do the sound class. And this is using some traditional approach to do the directional arrival estimation using DSP approach. So this will be lightweight enough for us to build into a so-called embedded style processor. Okay, as you recall, I mentioned about this competition. Back in 2020, they have this sound event localization and detection. So we use the SMN, sequential matching network, when we submit using their data, because they have common data for everyone to use, to train and to evaluate the performance. Okay, from this, we came in second in terms of team. Each team allows to have 4 submissions. All right, you can see that the first team over here is from China, I believe. This is our team from NTU. And we can see that the error rates is basically quite small in terms of classification errors. Okay, and this is the F-score, combining precision and recall. We have the F-score, the higher the better. And then we have the localization error, means that we get it wrong. We only have a tolerance of 9.3 degrees. The first one has 6 degrees and so on. All right, but it's pretty good in the sense that you can detect at around 9.3 degrees of errors. And the localization recall is around 90%. All right, so I have to move on. And we think that the separately trained approach may be good, but it's still not enough. So we look into a jointly trained approach. The jointly trained approach means that we have the data sets and go into a single neural network. We have a data set. We don't separately train for detection and localization. So in this case, the feature becomes very important. How can we extract features from this data set? And you can see from this diagram, this is a case of a time domain in the horizontal axis. And in this case, it's a frequency domain in the vertical axis. You can see there's lots of information that we can extract for us to detect what is in the data itself. So this is using the log-mel spectrogram. But when we want to detect the direction of arrival, you can see that we usually use a GCC FET to extract this information. But GCC FET is very plain in the sense that there's not much information can be extracted using the data set, because this data set consists of multiple sources. It's sort of confused and get into this type of very plain type of a pattern that it will not be helpful for the neural network to retrieve the data. All right, so it's not a very good features. And I have to move faster because I noticed the time is running short. Okay, so what we do here is that we introduce another types of feature called, a very nice name called SALSA, which stands for Spatial Q Augmented Log Spectrogram. So these particular features itself, you can see it extracted some of the frequency, time frequency information pretty well. And it also extracted some of the phase information, which is very critical, for the direction of arrival. All right, so but however, this feature is hard to compute because you have to create a spatial, so-called a signal covariant matrix, and you need to find the values from this matrix. So it's challenging, but for competition, we don't bother because we are not going for low cost and low. We just want to see that whether this technique works well or not. So in 2021, we participate. Again, we came in second, okay? And the first one is Sony. Sony has more manpower and more better machine than us. So we are very poor. So, but we came in second, respectable. In terms of error performance, in terms of localization, it's close. It's close. Using the method, just using the features. We can use some of the other types of neural network, very common like Google Net or other net style neural network. It still works well. All right. So we spend a lot of effort in crafting the features. And we find that this is very useful for us. So we came in second. And because we share the codes, they give us an award. Because Sony kept the code, they don't share it. Okay. So there's some features that we are very happy that we are able to find these features. And these are very useful to do detection and localization. And subsequent year, we come out with a lightweight version. We do simplification. Instead of creating the matrix, what we now do is to do some simple interchannel phase estimation. And this work has been published, and basically, it basically reduced the number of complexity by 30-fold. All right, so let me show you this demo. So you have you can see from this demo, we have speakers around the sensor box. It's over here. This sensor, this is using the microphone array plus the Raspberry Pi in the box. And we are playing speakers coming from different directions. I hope there's sound. 60 degrees. And you'll notice that this is our estimation. And then this is the class that we detect. It's shouting, 95, certain errors. It should be 90, but 95 degrees. Construction noise, 24 degrees, but it's actually coming from 30 degrees. So we want to test it, whether it can be used. This is engine revving. Okay. You can see sometimes the sound comes out, and then it sort of dies down. Then this thing will respond. You need to respond in real-time manner. All right? So we actually so-called implement this box and deploy it in an environment. So the advantage of having everything done in an edge device is that we can keep all the sensitive information, speech, whatever, privacy information in the box, because it'll be inferred in the box and be erased. So we don't send anything to the crowd. We only send the metadata, like the sound types, the pressure, duration, direction of arrival, the frequency of occurrence. All these are bite-sized data, very easily sent to the crowd. And we reduce the communication time as well in sending this type of bite-sized data. All right? And we do have an app to really see the whole thing in real time, because we are working with some government agency. They want to see that, they want to see all this information remotely. So they can open the apps, log into the IP address, and they can see all this information in real time. Okay. All right. And this is one of the deployment in Singapore. You can see that this is a unit. We put it in the walkway, a pillar under the walkway. And these are some of the sound classes that we detect. And it's not the distance, so do not mistaken that we can detect distance. We only can detect the general direction. It's not distant. And you can see that there are different colored dots representing different classes. Like alarm is all these pink colored dots. They are basically in the direction of a car park. So after we do it remotely, because we are not there all the time, once we detect a sound class, we save a snippet of this sound information, and we do a post-analysis on see whether we detect this. It's in this direction, there's an alarm. And it's most likely alarm because this part of the area is a car park. You have alarm coming from vehicles that park there. All right, and then some part is like a playground, a child care centers. we have we listen to it. We have different human voices at that area and so on. Okay, and this is the classification error based on our post-analysis evaluation. All right, this work was published in the IEEE IoT journal IoT. So if you're interested, you can take a look at this work. All right, so I just want to conclude the first part. I believe I'm seriously lack of time. I hope I'm okay. Because I need to introduce the sensing. We still got the control and the rendering. I'll be fast. Okay, this is a list of all the sensing challenges, low latency requirement, and the placement of the microphone when you train it, whether you do it jointly or separately, and so on. I'll leave it to you for your understanding. I'll move on to the control. So what is sound control? Like sound control is what you have used to it before. You can do noise control, you can do transparency listening, you can emphasize some of the sound to make it more prominent, and so on. So today I just want to touch on the active hear-through, the acoustic sensing. So these are some of the open headphones and closed headphone. The problem with open headphone is that we cannot do, okay, for open headphone, there's no need to do any hear-through processing because the sound is not blocked. You can see most of these, there are some earphones, they are just like those bone conducted earphones, those clip-on type earphones. They are not blocking the ear opening. All right, so we do not need to do any hear-through. The one that we need to do hear-through are the closed headphone. The ones is blocking the ears, occluding the ears from the environment. All right, this is also the type of headphone that is useful for us to do this augmented reality, virtual reality type effect. Because once you close the earphone, you can use microphones to pick up the environment sound and do further processing. Whereas this one, you have no control of sound that goes into the ear. Okay, so everyone is very familiar with this type of real sound control modes that you see from Apple apps device. All right, they have control like pass-through or passive without any processing. There's ANC, noise control, and there is also the acoustic transparency. This is the one that they want to do the sound as good as if you're not wearing hearables. Okay, and recently in iOS 17, they have this adaptive mode. So they are able to so-called depend on the environment you're in. They can help you to select whether you should have a noise control or hear-through or transparency mode. Okay, so if you look at the isolation curve of different types of hearables, you can see that at the top end, this is one from Sony. There's just an open earphone. This is not what we are interested in. There's another type is also open. And then, but we are more interested in those closed earphones. If you see the closed earphones, this frequency curve goes down rapidly after around 1 kilohertz. So it has attenuation of the high frequency contents. The low frequency contents are still untouched. You still go through without. That is where the active noise control comes in. You want to suppress the low frequency noise, you use the active noise control. All right, so how do we do we need to do some quick explanation, okay? Real sound, this is the reference. We want the sound to be this is what we want. We want the real sound to go into our eardrum without any obstacles, all right? But once you put in the earbud, you need to introduce some equalization to make the sound that you pick up is as close as the reference. All right, you need to have these features that's added in. So that is where you go through the hear-through processing. So I will quickly go through this part. We want this sound to be as close as a real sound, but as I mentioned before, there is also a leakage sound that goes through the earbuds without your processing, because the fit may not be correct, it may not be tight enough. So you can see you have this so-called leakage, which is represented by P, and A is the process signal. So when P and A meet, at this point, it basically causes a distortion. So this is what we call the comb filtering effect, which is undesired. And we are trying to solve this problem of reducing this comb filter effect. Okay, so there are many interesting techniques that goes on with this type of so-called compensation or equalization. For example, we can do the equalization of the headphones response, internal headphone response, and also doing this type of corrections. What we want to meet is the reference, but we need to subtract away the leakage and divide by the external sound they pick from the microphone. So you notice that this is signal processing techniques. We need to do all this type of equalization. So I think due to time, I will not want to say too much about this, and I want to move on to the last topic. Sorry about that. Because there are different techniques on doing so, okay? So we work on several techniques as well. The main purpose is to get a very seamlessly hear-through type effect. So, but if you're interested to know more about this technique, feel free to contact me. This is the one that's introduced, we call the least square techniques. So they work through some sort of optimization problem and find the best equalizer to that. I'll skip that. And then we work on some adaptive style algorithm to do this compensation while we are wearing the hearables. So this is a more so-called practical approach that you can do it in an in situ manner. Okay, but due to time, and then we have done some comparison with some of these earphones from the Sony and from other brands, just to see that our hear-through is comparable or even better than them. Okay, so, and then there's another group from Finland. They also do some sort of very low-cost device. It's basically a parametric equalizations to get rid of these occlusion effects. Because when you insert the hearables into the earbuds, it causes a certain shift in the acoustic patterns. It introduces boosting at the low frequencies. It reduces a null. It becomes a so-called a cancellation at the quarter wavelength, and it boosts up again at the half wavelength. So this will be, people will feel that it's not feeling comfortable while wearing this style hearable. So they do some parametric equalization to reduce the boosting, to introduce back the peak at this quarter wavelength, and to reduce the half wavelength. Okay, so this is just to make it natural, in a sense. Okay, so they come up with this simple approach. And again, for for real sound control, we are very concerned about the latency, the processing time to do this equalization. Okay, and also other types of changes in the coupling, changes in the environment, and so on. Okay, come to the last topic on how do we do sound rendering. This is the final part. Okay, for sound rendering, we need to consider how the human listen to sound in the environment. Because sound coming to you and to the human is being filtered by our head, our pinna, the ears itself. So this is what we call the head-related transfer function. So today I will just focus on this, but there are also something like environmental rendering you need to take care about, and head position tracking, equalization. But this is more interesting because if you look at our ears, even our left and right ears are not symmetric, are very different. My ears and your ears are very different. We have a ear print, like a fingerprint, are unique, or what we call idiosyncratic. Everyone has their own different ears, shape and size. And if you look at these are subjects' ears response, they play sound at certain direction, and they plant in binaural microphones attached to the ears. And you look at the response for subject 131 and 133 are very different. They have different dips at different frequencies and peak at different frequency. All right. So this is how the individual hears sound, directional sound. All right. So if you ask someone to listen to someone else's head-related transfer function, it will result in front-back confusions, in the head localization, timbral coloration, and so on. So usually when you want to play back some of this spatial sound using some generic head-related transfer function, you get all this type of problem. So it's very critical that we measure our own head-related transfer function. This is how we measure. We send someone into an anechoic chamber, and we have a cage full of loudspeakers, and he or she has to keep still while still wearing a microphone at the ear. You can see this is a binaural microphone. And they will pick up the sound coming from different directions, the left and right ears, and so on. All right? And this is your head-related transfer function at a particular location. And they will go around playing the speakers from different locations, and they will collect a whole set of head-related transfer function. Very tedious. You need people to be standing very still to collect this information. Another approach is to use a scanning device to scan the head shape and size, and use some numerical approach to derive this head-related transfer function. All right, so this is not that easily done, and it may not be accurate as well. All right, so this is just based on the geometry of the head shape and size. Another approach that some of the gaming companies are doing is that you basically train the user to recognize a certain sound from a direction. Because of our brain, we are able to train it in a manner. You just basically tell them that this is at 30 degrees, but this is maybe short term. And another approach now people are using is more machine learning approach. So they measure the anthropometry information of the ears, shape, how big is your head, what is the point-to-point distance of the ear shape and size, and so on. And they do some matching to their existing data set head-related transfer function. So they find the closest head-related transfer function to match to the ears. Okay? So this is what the companies are doing nowadays, like Microsoft, Genelec, Jabra, or even Creative Labs. So they take a picture. They take a picture of the ears. They compute all the different distance between the ears, shape, and size, and they come up with a head-related transfer function. So we did a slightly different approach. We do acoustic way, similar to one you see in the lab, but nowadays, because we got the head tracking device, we can ask the subject to move around his head, and we can track the orientation of his head, and this will give us the information of the head-related transfer function. So for example, this guy is basically using a goggle, or this head-mounted device, and inside he can see this image, and then as he go around his head, he's basically cover every direction that he's pointing to. All right? So we use some sort of very system identification approach to detect the impulse response for different direction. So, and this is being found to be quite useful. It may not be as accurate as the one in anechoic chamber, but it's good enough for it to do a fast in situ type of head-related transfer functions measurements. Okay, so this is the algorithm we use, is adaptive one, because it's turn his head, we are continuously computing the impulse response. Okay, and I think this will be more meaningful to show you. Okay, this is the speakers that is playing the white noise, and you can see that she's moving her head left and right, up and down, to capture the head-related transfer function for her ears. And then after we have collected this, we send it to the cloud for storage purpose. We use the Amazon cloud, and we store the head-related transfer function, and then we play back. We use her head-related transfer function and convolve with all the sound, and as she moves around, she's using her own head-related transfer function to play back. And if she's using others' head-related transfer function, the effect will be very different, will be very in-the-ear type of thing. All right? So it's like end-to-end systems that we can do it very rapidly, capture and play back. Okay? I think you can hear the difference, but you need to wear the headphones to hear the difference. Okay? All right. So we also do other experiments, because when we are doing this type of acoustic measurement, it's very easy for us to we can conduct experiments to say that we can have head and torso at the same direction, or the torso is always facing straight, we move our head. So we can come up with different types of experiments to see how these head-related transfer are being modified. Okay? and so on. So we also investigate some of these head-related transfer for different headgear, like the one from Microsoft, HTC, Oculus, and so on, to see how much of the difference each headgear has introduced to the head-related transfer function. All right, but due to time, I cannot say too much. Right? But in summary, so it's very important that we acquire these individualized head-related transfer functions, okay, for us to play back in a realistic manner for the individuals. Okay, so conclusion. So I hope I've introduced the signal processing and AI techniques to do sensing, control, and rendering. And it's very important to take note that this hearable is very personal. So we need to have a bespoke solution for individual. And this is very so-called useful for perceptual AI. When you wear the hearables, they know what's happening, they know your profile, they know your preference, and they can use these informations for subsequent playback. So they can learn what your preference is. All right? So this is just a statement to say what is still a lot of work to be done to give you a very seamless integration of sound, especially virtual and real sound. And then there are still many questions. I will skip this. I want to come to the last part. Challenges. There are still many challenges because when you're doing virtual reality, augmented reality, the timing, the processing time is very critical. For virtual reality, the latency can be, motion to sound latency can be around 70 to 100 milliseconds. Augmented reality is around 30 milliseconds, less than that, because augmented reality is the real and the virtual sound together. Okay, and then the power consumption is, of course, important because everything is done in the hearables. You need to have a processor that is low cost and also low power. All right, so real-time interface. And I like this statement because this is from Spider-Man. It says that with hearing, with superpower in hearing, super hearing, it comes great responsibility because we can now, the privacy and the security issues is becoming important because you know more information environment, how do we protect this type of privacy and security. And for deep learning, as I explained in the previous talk in Twin Cities, people are asking explainable. Are you able to explain that your model is doing the right thing? Okay, just like this case is an experiment that they done in Germany. This horse is basically able to do some arithmetic or you can do some spelling, but in fact, it is taking the cue from the trainer. So this is a clever hands. So it may be the same thing as the neural network. It is not actually doing the thing that you thought it's doing. All right, so we need to explain the models. I think that is very important. And finally, when we come to all this perception, listening, there's always the case that if we train it very specifically to a certain direction, we may incur some distortion, loss of quality, or what we call the timbral performance is degraded. So when you do something well in localization, your timbral may get worse. So how do you balance it? Which should come first? So usually people will want to have the quality as good as possible. Timbral will come first, followed by localization. Okay, this is my final slide. And this slide is very interesting. This is coming from IEEE Spectrum magazine in 2019 by Poppy Crum. She used to work in Adobe, I believe. Adobe. And she has this very interesting remark that the ear is a biological equivalence of a USB port. It can detect the internal features, internal biosignal of the human, and also the environmental signal. So it will be coming to a time where the intelligence will know what you are feeling, how you are feeling, and they will respond to what is in the environment as well and play back something that will calm you down or make you more happy and so on. So you can see over here there are many different types of applications that can be built into the hearables. All right, many interesting application. So it opens up many opportunities in research and also commercial product. So thank you a lot for your, thanks a lot for your attention. Yeah, apologize that it overstretched the time. Thank you very much.
Much, Professor Gan. That's the talk covered lots of very interesting topics. So I think we're a little bit running out of time, and probably just 2 or 3 questions from audience. Questions from audience?
Yes.
What is typical time processing? Milliseconds, microseconds?
It's in the millisecond. For example, the hear through, we try to keep it in within the 1 millisecond. But this may be challenging if you want to include other components like AI. So the approach may be to decouple some of this intelligence outside the hearables. For example, running in the smartphones, running in some crowd, if can, and then sending whatever important information to change the status of the earbuds. All right, so that may be the approach, because if you put a very heavy-duty chipset into the hearable, it's going to have the computational cost, the price, as well as the power consumption. All right, but we're not saying that it never happen, because the chipsets are getting better, less power, more processing power. Okay. But I think currently the approach may be to decouple some of the heavy-duty jobs to another processor, so that we can meet that latency that we demand. Yeah. Thanks.
Any other questions from the audience?
Sure. Yeah, I mean, we don't, because the sound is unstructured data set, and normally we will first of all formulate that's features. We need to come up with the features, all right? Because it's not like word by word you can have tokenized, because sounds are a bit complex. We don't know what we have to put into features before we can extract the features and do some separation. Once we got the metadata and all these things, then we can sort of put it into another stage for the large language model to take on, coming into like a word form, describe like what you see from here is what type of noise, where is it coming from, and these are basically like information that prompt. You can prompt the LM to do that. Usually, yeah, it depends on the real-time needs on it. It may be a few hundred of a millisecond, because we take frame by frame. We are taking frame by frame. We are not taking sample by sample. Okay, because all this neural network needs to have a frame to form the pattern. Then we can do the FFT, as you know, or the spectrograms. We need a frame. That, yes. It's a time domain frame. You chop it out, and then you do the. Yes, there are overlaps. Usually a 50% overlaps. Yeah.
Okay. Any other questions? Probably the last questions. Okay. Yeah. Maybe I can ask you questions about edge computing there. So you said because of the hearable, right? Some mobile devices, you need to. The model, say the deep learning model or something, you need to restrict the size of model so you can deploy to the mobile devices using edge computing, those kind of. I'm just wondering, so say for your model, the training to classify the different type of the sounds and the directions, I just wondering how, because it's a limited size of model, whether those edge computation need to limit the power of the deep learning models. I mean, if you're just using supercomputers to do that, you can have very high accuracy.
Yeah.
But
yeah.
if you're applying to the edge computing because of the limitation of the resources, what's your performance?
Yeah, we didn't say much about it because we need to do sometimes quantization, pruning, all these to make it small enough. But I would say that the processors is getting better. The previously, when we started this project, we are using Raspberry Pi 3. We can still do some of the models are smaller, but now we have Raspberry 4. We can do much better, much bigger set of model, and it's getting more powerful. So even in those type of processing board, no, it doesn't need to be supercomputers. Okay, so it's getting faster and better at a lower cost.
Okay, so the performance that's not...
Performance, I think, will be sort of, it get better. And of course, we always need to do some quantization and pruning type of steps to make it into a size that can fit into the memory as well as the processing.
Right. Okay, thank you.
Thank you.
Okay, okay. I think thank you again for Professor again. If anyone interested in
my
speaker,
email is there.
Yeah. Okay, thank you very much.
Thank you. Thank you. Thank you.